We're going to finish 3.5. We had looked last time at some models for division, and talked about the fact that all these wonderful properties that we had for multiplication all fail for division. And now we're going to look at an algorithm for division that you know and love, so to speak, and an algorithm for division that maybe you haven't seen before as well. So the first algorithm that we're going to look at is the standard algorithm, the one you know and love. And we'll work through it together and kind of talk through how kids are typically just, walked through how to do the problem. So we have 623, and we're wanting to divide it by 5. And the language that corresponds to this is usually something like, we take the first digit and we ask ourselves, does 5 go into 6? And if the answer is yes, we say how many times? So the answer is yes. And how many times will 5 go into 6? Once. So we write a 1 above the 6. And then we do 1 times 5 when we get 1 times 5 and we get 5. The subtraction gives me 1. You were a step ahead of me already, I can tell. And then we subtract. We've got a 1 left over. And then maybe you have somebody who draws an arrow to bring it down. Maybe you don't, but that's one way of doing it. So we pull the next number down. If for some reason at this point this number is still bigger than 5, it just means you didn't choose the right number in your quotient, right? You didn't divide by enough. For example, if you looked at 12 and you said how many times does 5 go into 12, and you said 1, I'm just going to show you something wrong for a second so you can see what I mean. And you put a 5 here, and then you subtract and you get 7, and this number is bigger than 5, then you haven't actually done the biggest value possible. Are you with me? Okay, so and it happens. Kids will do that sometimes, just so you know. So it shouldn't be 1, right? We would go backwards and we would do, say it's 2. So 2 times 5 is 10. And we subtract and we get 2. And then we bring the 3 down. And we say, how many times does 5 go into 23 now? 4 times. 4 times 5 is 20. And we subtract and we get 3. And for the purposes of what we're doing right now, we're looking at leaving numbers with remainders. This is 124, remainder 3.
I see.
Okay, and this goes clear up to 5th grade. My 5th graders are still doing remainders on numbers. They're not doing fractional. They will be later this year. I know they will, because I can see the progression in the work that they're doing as they bring it home. But right now they're still doing remainders. So this goes clear through 5th grade, okay? At least in the curriculums that are currently being used. Now, some things to be aware of about the standard algorithm is that you absolutely had to know your multiplication tables to do this problem, didn't you? Yeah. I mean, you really do. So if you've got students who have difficulty with memorization and there are learning disabilities that cause that, the standard algorithm can be very difficult. The other thing that was really nice is that we divided by a single value 5. So in this whole idea of knowing multiplication tables, it's nice because it was 5, and you learned your 5s tables somewhere along the way probably, right? What if the number you'd been dividing by was 54? Well, that's messier because I didn't ever learn a 54's multiplication set, right? So there's a couple of things that make this easier than others. One is that it's single digit, and one is that we know our multiplication tables. So I'm going to show you the other algorithm with this example, just because I already have it, but recognizing that this isn't really like the worst one ever to do the standard algorithm with. There are others that are worse. But let me show you what the other algorithm looks like. So this other algorithm is called partial quotient scaffold algorithm. It's going to take me a while to get used to that because they changed the name of my algorithm. It's not what this has always been called in this book. So here's what this algorithm does. This algorithm uses subtraction instead of multiplication. Okay, so we had to know our multiplication tables, right, to do the last algorithm. But what this algorithm does is it puts a 5 in as big a place value as it can, which would be the hundreds place, and zeros. So essentially I've done 5 times 100, and I'm going to write these out to the side to remind ourselves as we go what we've actually done. And what we're really going to do is we're subtracting 623 minus 500. And the numbers we subtract will always be the number I'm dividing by with zeros attached at the end. So if I were dividing by 54, I'd either subtract 54 or 540, that's 540, or 5400 or 54,000 or 54 million. It would always be 54 with zeros. Okay? So 623 minus 500, and I would get 123. Now I can't subtract 500 anymore. It's too big. So what's the next thing I would be able to subtract? 50, because it's always 5s with zeros attached. But 50 is really 5 times 10. Agreed? Okay, these are going to always be powers of 10 over here. If you're trying to write me something that doesn't have a power of 10, you've got the wrong value. Okay, so what is 123 minus 50? 73. Can I subtract 50 again?
Yes.
Yep, I can. So again, 5 times 10.
Oh.
Okay, so what's 73 minus 50? 23. Can I subtract 50 again? No. So what can I subtract? 5. And 5 is really 5 times 1. Okay, so 23 minus 5 would be 18. Can I subtract 5 again?
Yes.
Yep. So this is 5 times 1. 18 minus 5 would be 13, and I've run out of space, so I'm just going to move over here. I'm just doing a whole bunch of subtracting anyway, right? Okay, I can subtract 5 again. What is 13 minus 5? 8. And I can do it one more time, right? And I get 3. And at 3, I'm stuck because the 3 is now smaller than the number I've got the lowest value of subtracting. Everything that I highlighted in yellow, I was doing that for a reason. That's your answer. 100,
That's what I was like.
20, 1, 2, 3, 4. It's 124. Remainder 3. Okay, so again, this division by 5 was not so awful to do in the other problem. But it does a really nice job of working with kids whose memorization ability, through whatever reason it is, isn't really there. Maybe it's because they are having true difficulties with memorization, or maybe it's because we're dividing by 54, and so division by 54 is like awkward, and I don't have a very good algorithm for doing that efficiently, and I do a lot of trial and error as I'm working through a standard algorithm with it or whatever. So we end up getting 123. Now, this is not especially friendly if the number ends up having to be multiplied, or not multiplied, but subtracted a lot of times, right? If I subtracted the number 5 off 9 times, you guys would all be like, seriously, correct? Be messy. It would be tedious is what it would be. It would be tedious. Okay, so there are definitely some drawbacks to this too. It's also just in general a lot of steps. I mean, it is. It's a lot of steps. But intuitively, it works very nicely. What this did is it said that I have, one group of 500, and I have 2 groups of 10, and I have 4 groups of 5 when I'm done. I mean, it works really nicely for some conceptual components of this. All right. It's in later in the questions. Your box question, I'm going to do another one like it. It's just in the next lesson. They switched the sections around. Okay, let's look at a few application problems. Some of them I'm going to do different algorithms with. Some of them I'm going to do standard algorithms with, and we'll take a look as we go. So we have Juan. Juan saved $5,340 in 3 years. If he saved $95 per month the first year, and then a fixed amount per month during the last 2 years, how much did he save per month during the last 2 years? So this is a multi-step problem, if you will, that involves more than just one type of algorithm. So what do you see? Well, what kind of things might you want to do first on Juan's problem?
95 times 12.
95 times 12. So what is 95 times 12? I don't mean what numerical value, but what conceptually is that going to achieve for us?
So that's how much he saved in the first year.
Right, so this is the amount saved in year 1. Okay, is everybody good with that? All right, so for fun, we're going to do that with the lattice algorithm because we didn't do very much of those last time. So we have 9, 5, and 1, 2, and we divide our boxes along our diagonals like so. Nothing in this problem said I had to use lattice algorithm, so if you don't want to, you don't have to. But we're just practicing. Okay, so, well, 95 times 1 is 95, so that's, nice. All right, so how about 9 times 2? 18, so that's a 1 and an 8. And then 5 times 2. 10, so it's a 1 and a 0. And then if you remember the way this works is that we extend our diagonals like so. We start with the bottom right-hand corner, 0. And then I look at the pieces that are inside of the lattice. 8, 1, and 5. So how much do those add up to? 14. So I write down a 4 and I carry my 1. And then I add up the 1, 9, and 1, and I get, what did I get? 11. So I do a 1. I technically would carry a 1, and it would be in this next placeholder over here, but there's 1140. Okay, so he saved 1140 during his first year. So what do I do next?
Subtract that from the total amount he saved every year.
Okay, he saved 5340, and we're going to subtract 1140. The nice thing about that particular subtraction is that it doesn't involve any regrouping or anything like that. So very concretely, I could just do it as a standard algorithm or left or right. It doesn't matter what algorithm almost that I use because there's no borrowing involved. So I actually have $4,200. So this is the amount that he saved in years 2 and 3, right? Yeah. So then what would I do?
Subtract it by 24.
Yeah, I need to divide it by 24. Now, I'm going to tell you that my intent was to show you how to do the division by 24 with the repeated subtraction here. It's in my notes even to do that. For the sake of time, I'm not going to, and the reason is because it's very long on this particular one. But it's one of those ones where it would be a nice one to do it with repeated subtraction because 24 is not a multiplication table, But for the interest of time, let's take a look at what happens with the standard algorithm. Now, the reason that this with the standard algorithm is a little confusing, of course, is because what students are typically told is that they look at this 2 and they look at this 4, and they say, how many times does 2 go into 4? And the answer is 2. But if you put a 2 above the 42, then you get 48 here. Are you with me? What's wrong?
Would it be divided by 12?
It's the last 2 years.
Oh, okay.
So yes, that's a good question. We have 2 years worth of data values. Now what you could do, Annika, is you could divide by 12 to find a monthly and then divide by 2 again. So that would be another possibility way of doing it. Okay, so, right, like this idea of looking at the 2 at the beginning and the 4 at the beginning of the other number, it works sometimes, but it's a little bit of trial and error because we don't have a multiplication table by 24 sort of tucked in the back of our mind. So when we have this happen, what ends up happening a lot of the time is that we have to retry something else and say, well, that was too many, so I'm going to try it again. It must not go in 2 times. It must only go in 1 time. So then I've got a 24 subtracted here instead. So what is 42 minus 24? 18. And again, that's kind of messy. I mean, like 24 going into 180. It's a little bit of guessing, right? I mean, I can't just look at the 2 and the 18. It's going to be going 9 times. It's too many because it's not 20, it's 24. So any idea of what we might want to try? 7. So 7 times 4 is 28, right? 7 times 2 is 14 plus 2 is 16, so I have 168, which gives me as a remainder, what's next? What do I have to, when I subtract? Maybe I didn't use the right word. When I subtract, what do I get? 12, right. And then I will bring the last 0 down, and I would ask again, how many times does 24 go into 120? And the answer is 5. 5 times 4 happens to exactly be 120, which is great, to give a remainder of 0. And the reason why the repeated subtraction on this one is so long is because I have to subtract 247 times in the problem. And then I'd have to subtract the number 24 5 times in the problem. So the number of subtraction steps is quite lengthy. However, there's trial and error involved if you don't. So, 12 one way, half a dozen, or a dozen the other, right? I mean, it's just not a simple problem like the division by 5 one was. So the answer to the question is $175 per month those last 2 years. And do you see the next problem, Danielle? It's about pennies, but it's about boxes. This is the problem I was remembering when I was answering your question. Dan has 4,520 pennies in 3 boxes. He says there are 3 times as many pennies in the first box as in the third box, and there are twice as many in the second box as in the first box. How much money does he have in each box? So slightly different question, but similar idea. They have 3 boxes, so a visual is a good idea. And it says that there are 3 times as many pennies in the first box as the third box, and it's all relating back to this third box. So we'll just put an arbitrary X in box 3. And it says there's 3 times as many in box 1. And it says there are twice as many in the second box as the first box. So how much is in the second box? 2 times 3x or 6x, right? So this is 6x. And then what I'm wanting to do is I'm wanting to figure out how much money's in each box. Well, when I combine all the boxes. So I have 3x, pennies in the first box, 6x pennies in the second box, and x pennies in the third box, for a total of 4,520 pennies. And 3 plus 6 plus 1 is 10. So this is 10x on the left, 4,520 on the right. And then what would I do? Divide by 10. So what will x be? 452. Now what does 452 actually mean in the context of the problem? Okay, so it means that there's 452 pennies in box 3. So it's equivalent, so this is the number of pennies. So it's equivalent to having $4.52. Does that make sense? And that's box 3, but the question actually asked how much money does he have in each box. So we just found out that box 3 has 452. What would you do to get box 1 and 2?
Just plug in X.
Yeah, so you can take 452, I'll do it down here, and multiply by 3, and 452 and multiply by 6. So in box 1, 452 times 3, how much money will I have? 1356. And then in box 2, what will I have?
$27.12.
I agree. Okay, are we good? Okay, the last part of this section is about mental math and estimations. So one of the mental math strategies that works out really nicely, and these are both breaking up the dividend, but they're done slightly differently, problems 6 and 7. So if you take a look at 6,318 divided by 9, and you break the numbers apart, there's a very nice break in these numbers that's evenly or easily divisible by 9. So how could I break the numbers apart?
Oh, 63.
Right. So 63 and 18. So what I'm going to do is I'm going to write them broken apart, but 63 is, of course, 6,300, and then 18 is, of course, 18. Okay, so whether you're actually, this is mental math, so you're writing it down for my benefit, not because your brain can't do it. I get that. But if you did 6,300 and you divided by 9, what would you get? 700. And you did the 18 divided by 9, and you get 2.
I was like 9.
So yeah, 702. So this is one where the visual for it is already multiples of 9, so it makes it really nice. The next problem isn't quite the same because, I can't break this apart into 4 and 25, or into 42 and 5. Neither of those are each sets divisible by 5. But I kind of can. Yes. So instead, although 4 is not really working, 400 works great, right? It does. So what is 400 divided by 5? 80. And 25 divided by 5? 5 for 85.
Oh, that's nice.
It is nice.
I like that.
So obviously this doesn't work for all numbers. Like, I get that. That's not the point. The point is that when they are numbers that for which it does work, utilize the skills that you have because it's going to make your life easier. All right, the last question is about estimation. So this is compatible numbers. If you were to try to break this apart like the last problems, it doesn't work very nicely. 41 and 32 are not nice. 32 is fine, I should say that. 41 is not so fine. And it doesn't sort of become fine any better with anything else. Like, I can't break it apart into the 4 and then into the, I mean, it's just messy, right? I mean, this is messy. So this question's not actually asking you to find the exact answer. It's asking you or showing you a strategy for estimation. Okay? So mark yourself on your paper when you circle that this is an estimation strategy, please. The idea is to make the numbers compatible. And if you remember what we've done with compatible numbers all the way along, is we actually change numbers to make the math work out easier. That's the goal. And the numbers are compatible when the math is easy to do. So we don't want to change things drastically or the answers are not close and it's not useful. We want to change them slightly to make them useful. So, but easy. So what are numbers that would be, what is a number that would be more compatible with the number 4 than 4,132? 4,000 would be much friendlier, agreed? Yeah. So this is going to be approximately the same as 4,000 divided by 4. And what is 4,000 divided by 4? 1,000. So this is an estimation technique where I'm changing the numbers slightly to get something close. Okay? Any questions on that? All right.